Okay, we're back online. Great. So like I was saying, optimization, too big of a topic to cover in just one class, but the stuff that we do cover today should hopefully at least familiarize yourselves with kind of what optimization is, how to formulate it, and then you can use kind of solvers to actually perform the optimization. And I'm going to try and give some like caveats and things to be careful about when doing something like that. Otherwise, definitely, if this stuff is of interest, definitely take a class to kind of formalize how to do this. And there are many classes that cover different aspects of optimization, of which hopefully you'll be familiar with again at the end of the day. So there's a huge number of things that are built on optimization, right? And so what are we talking about exactly? So optimization is the idea where we can find the sort of best available values to achieve some specific objective. And so most often over some kind of set of constraints. Okay, and so we'll formalize this a little bit more. But here are some signs that your problem could be an optimization. You know, how do I mitigate emissions at the lowest cost possible? How do I maximize profits related to energy production when following regulatory requirements? How can I drive a plug-in hybrid with the most electricity possible? How can I minimize downtime for Uber or Lyft drivers? So the key thing here is if you are doing the most or the least of anything, that's a pretty strong suggestion that the type of problem and the type of question you're answering is based on an optimization. Okay? Any questions? All right, so canonical form of an optimization we call negative null. And there are kind of three things to watch out for, okay? So one, we're going to minimize the objective function, okay? And so when we talk about maximizing or minimize something, this is the actual thing that you're going to be trying to minimize or maximize. Okay, and so in this previous example, right, our objective function would be something about the cost, something about profits, something about the electricity consumption, and then something about downtime, right? And so that's, all of those are talking specifically about that objective function. You have a set of what are known as decision variables. And so these are actually the things that are allowed to vary so that your objective function can be increasing or decreasing, right? And this could be, but not always, subject to a set of constraints. And constraints are ways in which I can limit specific aspects of the problem. It might be with the decision variables, it might be with other pieces that might relate to decision variables. So we'll look at a couple of examples of this in a little bit. To talk about that very first one, this might be an example of a formulation of an optimization where I say, okay, I want to minimize the total cost, and the total cost is equal to the amount of energy production times the marginal cost of any particular technology, right? And so depending on how much energy I produce, there's a cost associated with producing that technology or producing that energy from every technology. And if I sum all of that up, I'll have some kind of total cost. And the basic idea is I can change. So we say with respect to WRT, that's talking about the decision variable. So I'm allowed to affect the energy production for like different technologies, right? And so here, if I'm trying to minimize this, so ignore this for a second, who can tell me what value I should be putting in for energy production in order to get the smallest total cost possible? Zero?
Yeah, 0.
Yeah, so close, but actually this is totally unconstrained, so actually I would choose negative infinity, right? And so that would technically minimize my total cost. And so in this particular formulation of our problem, I actually need to put something about some kind of limitations on my decision variable in a constraint that will make it so that, oh, you're not actually allowed to, be less than 0, right? And so you might have a constraint that says energy production has to be greater than equal to some amount of demand, for example. And that would constrain it so that you would want to produce some positive, or you would have to produce some positive amount of energy. You can also have other constraints, like maybe I have some regulation that puts a limit on the amount of carbon that you can produce. And so different types of energy productions will have carbon emissions associated with them, and they have to be less than some kind of carbon limit. Okay. So this is just kind of a high level example that's showing the sort of general structure where you always are going to need an objective function and decision variables in your optimization, and then oftentimes you're going to have constraints in the optimization to kind of help bound the problem. Okay? So that's a way where we can start thinking about different categories of optimization. So if I have an optimization that is, so minimize this function, right? This is our objective function with respect to x. There's no constraints, and so we call that an unconstrained optimization. You can also have these three, which are forms of optimization where we actually include constraints. And you can have what are known as equality constraints, where basically you have an equal sign in your constraint. You can have inequality constraints where you have less than or equal to or greater than or equal to in your constraint. And then you have a general constraint optimization. So hopefully that's pretty straightforward. Now the reason why we kind of divide these into sort of different categories is actually the math behind solving these has a whole sort of different set of nuances that we have to think about in depending on the way that our optimization is structured. Okay, so that's the sort of primary reason why I'm categorizing things in this way. The other thing that is important to think about in an optimization is something known as convexity. And so as it relates to the functions in your optimization, so the objective function and or the constraints, convexity is a really important property that tells us something about both the way that we solve it and kind of the confidence in our answers. So convex function, this is like our bowl shaped, right? So if you take a line between any 2 points of our function, and so suppose this f of x is our objective function, okay? So if I take any 2 points along this line, the line between those 2 points lies above the function. In other words, if I can draw a point between a straight line between any 2 points that doesn't go through the function, then that's considered convex. Okay, so is this a convex function? No, right? Because I can go from here to here, and if I draw a line, it would pass through the function itself, making it a non-convex function. You can also have what is known as a convex set. And so this might be defined as a function that's relating two variables in a constraint. And so if you map out the coverage of that set of points, it's a similar type of analogy. If you can draw a line segment between two sets and any of the points lie outside of that set, then it's not convex. So these are both examples of non-convexity in your optimization. Okay, and again, the reason why I talk about this is because it classifies our problem in a certain way, and the way that we solve the problem is going to change. So if you guys think back to calculus, for example, what does a derivative tell you in reference to a function? What does the derivative of a function tell you? Yeah, the slope at any particular point, right? And so one of the ways in which we solve an optimization is you essentially, so this is kind of like a high level way of thinking about this, is essentially I look at the derivative, I look at the slope, right? And if the slope is positive or negative, right, it means that any direction that I go along that slope, I'm either increasing in value or decreasing in value, right? And then what's the derivative at this point here? 0, right? It's flat. And so basically, a lot of optimizations are looking at these slopes and taking you in a direction to get you towards 0. And the reason why convexity matters so much, right, is if I want to find the minimum of this function, and I come over here, I'm going to be able to, look at my derivatives, see that it's 0, look in both directions, see that it's going up, and say, oh, I found a minimum. But this might be not the right answer, right? So there are local minimums and global minimums. And so a local minimum is better than its neighbors, and a global minimum is better than everything. Okay, and so one of the properties of the optimizations is that optimization solvers is that if you have a convex function, it's a lot easier to find a global minimum because any local minimum in a convex function is your global minimum, but that may not be true for a non-convex function. Okay? And so you'll want to think about these things, if you have an objective function that is non-convex, you might have to think carefully about whether or not you've actually gotten the sort of quote-unquote right answer. Okay?
An example of that type of function?
Yes. So x to the third power, right,
How would you
is...
see this in like a more applicable type of...
Yeah. Well, any cubic function that may arise. So if it so happens that let's say I don't know, like a heat rate for a power plant is has a function that looks cubic, theoretically, right? And you were saying, oh, I want to minimize the cost of the operation, right? You might, if you just plugged it into a generic solver without understanding the sort of non-convexity of the problem, it may actually give you the wrong answer because it might find incorrect local minimum, right? Yeah. What is I mean, I don't know if I can come up with a more concrete example right off the top of my head, unless someone else here.
I was thinking fuel efficiency.
Yeah.
That you have set out.
So wait, sorry, fuel efficiency what?
I've done it before where it's kind of like looking at fuel efficiency over like a distance traveled,
Yeah.
kind of looking at it was mapping it with, I forget, I think with the cruise control. It's like trying to gauge a certain speed that it had to maintain at as well.
Yeah, yeah. So it's not uncommon for functions to be non-convex. Uh,
I'm thinking maybe like ozone generation versus VOCs. And
Ye-
that kind of like if you were mapping ozone. 'Cause
Yeah.
I know it can do that.
So I guess what
I'm
I'll
trying to think of like an example of like where it would have double dip like this right now. And then I'm just like.
well, a double dip like this might be a little bit less common. They get so what I would say is this is a very easy example where I could just graph out the objective function and see visually that I have like multiple minimum. That is not typically going to be the case for you to be able to visually say that it's a non-convex function. Oftentimes, you're going to have to show that it is convex sort of mathematically, and the reason for that is oftentimes you're dealing with like a large set of like decision variables, whereas this is just like one dimension, right? It could be across many dimensions that the non-convexity shows up, right? And so you can mathematically show that a function is non-convex. Yeah, and so oftentimes it's not going to be this like visual representation of the non-convexity.
Okay.
Yeah. Okay. So to further give more complexity into optimization, this is an additional sort of breakdown of classifications. So we talked about whether or not you have specific types of constraints, right? So if you have your equality constraint, inequality constraint, or general, what did I call it? The general constraint optimization, which has both. You also have optimizations which are entirely linear, okay? You have optimizations which are convex, and then you have optimizations, so this convex nonlinear, right? So you have basically x squared. I guess there are technically other types of convex problems, but usually, they're sort of x squared type things. And then you have nonlinear, which could be a non-convex type of problem. And then another way to sort of break this down is for our decision variables, x, right? So these are variables that you're like modifying in order to try and solve your optimization in order to minimize or maximize something. And your x could technically be continuous, or it can be an integer problem. Can anyone think of an example of an optimization that might be integer based? Yeah.
I think many problems where you have like a capital investment at the beginning, and then you have like a 0 or 1 variable where you were investing that capital and building something.
Yeah. So I was thinking of so Paco that did the
The mines.
opening the mines,
Yeah.
right? And so that's like, so he was doing an optimization where you do an investment into whether or not you open or close a mine, and you can represent that as like 0 or 1s, right? So that's not a continuous thing where it's like partially open, it has to be 0 or 1. Another example of an integer problem that I've done before is for like If you're simulating the operation of like the electricity system, power plants can be on or off, so that's a 0, 1, and then if they're on, then you might have a continuous thing of like how much they're operating. But there's a important thing to track whether or not they're turned on or off. And so you represent that as an integer. And so integers are, I would say, sort of notoriously a little bit more difficult to deal with mathematically. And then so a mixed integer program is where you are having decision variables that are both continuous and integers in your problem. So generally speaking, the more you go down this way, the more complex, and the more you go this way, the more complex. Yeah, so if you're in the world of like mixed integer, nonlinear programming, those are like computationally the most difficult to solve, the most computationally intractable. I had to do a bunch of this stuff in grad school, and I haven't touched it since. But I do a lot of mixed integer linear programming. Yeah, and so keeping things linear if you can will oftentimes make it a lot easier to solve. The world of linear programming is very, very well developed. The algorithms and solvers to do this stuff is very, very fast these days. And kind of the more you go towards here, yeah, generally speaking, the harder it's going to get. Yes?
What is an affine function?
So affine, yeah, so this is like a particular mathematical property of the functions. Okay, I kind of don't want to get into the specifics of what defines because I don't want to confuse people. Yeah. Just know that is a particular property of the functions that will let you determine whether something is convex. Yeah. Okay. So let's do a little example here. Okay, so you run a milk and cookies operation. Okay, a cookie costs 25 cents to make, and then you purchase milk from a wholesale distributor for 10 cents. After you've hired a marketing team, you've determined that the quantity of cookies, which we'll call Q1, are in demand as a function of the cookie's price, right? So this is like a classic economics example. So the demand for the cookies is based on, so that's equal to Q1 equals 0.5 minus P1. You've also determined that the quantity of milk is in demand as a function of the price of milk. And so that's Q2 equals 1 minus P2. Okay, so my question to you guys would be, knowing all of this information, what prices would I set to maximize my profits, right? And so I know what my costs are, and I'm the one who actually sets the price. Who can tell me what are my decision variables? Yes. P1 and P2. So I'm deciding what prices that I want to set my milk and cookies, okay? And so those are not set in the problem in any way. That's something that I decide. So that is my decision variable. And so what is my objective? Yeah.
To maximize profit, which would be the price times the demand for each minus the cost.
Yeah, okay. And so we know my objective, right? We identify that by looking at the word maximize or minimize. And so this case is profits, and profits are how much money I make, which is, it's P times Q, right? That is the price times the quantity. And so every unit of quantity that I sell, I get some money based on the price, minus the cost associated with each of, with the cost associated with getting that cookie or milk, right? So let's sketch that out real quick. All right. Oh, I can't even see my thing anymore. Okay, that's all right. So profit is equal to P1 times Q1 plus P2 times Q2 minus, oh, is it not? Hang on, sorry. There we go. All right, and actually, let me do it this way. We'll say Q1 times P1 minus the cost of producing. P1 was 25 cents, so 0.25 plus Q2 times P2 minus 0.1.
Yeah.
Okay. And we want to maximize this. So this is going to be equal to, what was my, what were my demand functions? 0.5 minus P1 times P1 minus 0.25 plus 1 minus P2 times P2 minus 0.1. Okay? And then in negative null form, we are going to minimize the negative of this whole thing. So negative of 0.5 minus P1 times P1 minus 0.25 plus 1 minus P2 times P2 minus 0.1. Okay? And this is with respect to P1 and P2. Great. So this is how we would set up the optimization. Okay. So who can tell me what type of optimization this is? Yeah.
Well, it's definitely non-linear because you're multiplying the piece with each other.
Okay. Is this constrained or unconstrained?
That's unconstrained, but maybe you would include like a non-negativity. But it doesn't really matter because you're like not choosing a negative price anyways, because then you will reduce.
Yes, in this, yeah. So this is a totally unconstrained. You don't actually need to include anything about the prices because it's actually set up in such a way that right, with a classical like economics definition of quantity and price relationship. So it'll certainly be, the prices will always work out to be positive. And that's right. So this is an unconstrained, non-linear optimization And then, is this optimization convex? What do you guys think? In this particular case, it is. You're only dealing with squared terms, and so it ends up being convex. But again, hard to visualize even with 2 dimensions. So if I if I simplify this out a little bit, we end up with this form, right? So we were here, and I just simplified the form to write out like this. And so we have, we minimize the negative profit, which is the same thing as maximizing the positive profit with respect to P1, P2, where profit is equal to P1 squared minus 0.75 P1 plus P2 squared minus 1.1 P2 plus 0.225. Okay? Okay. How do I solve this problem? Yeah.
Take the derivative of derivatives and
Yeah. So right now we've got one equation with 2 unknowns, and technically speaking, right, our P1 and P2 can take on any value, but the value that we want them to take on is what happens when your derivative is equal to 0, right? That's how we calculate that the slope is equal to 0. And because this is convex, that will only happen at the global minimum. So if I take the first derivative and set it equal to 0, that tells me what points are at my local maximum or local minimum. So in this particular case, if I do the derivative of my objective function with respect to P1, and then I do the derivative of my objective function with respect to P2, I'll end up with 2 times P1 minus 0.75, right? Because P1 squared, derivative is 2P1, and then 0.75 times P1, and then the constant goes to 0, and same here. And so I set these both equal to 0, and then I can solve for my P1 and P2. Okay, so if I were to set my prices at these values, that is the most profit that I can make, okay? And in fact, you can go back and you can like graph this if you want and see how your profits change as a function of your P1 and P2. And yeah, and this is the value that's going to give you the highest profit. Okay, so technically speaking, you want to check that if you're at a local minimum versus a local maximum. So you can take the second derivative, and if it's positive definite, that indicates the solution is at a local minimum. And so this is the type of stuff that you might kind of cover in an optimization class about like checking kind of all your bases. In this particular easier example, right, we're just taking the second derivative with respect to each of my variables, and then we're checking our eigenvalues. And in this case, it is greater than 0, and so this is happening at a local minimum. That's kind of what this whole bit is covering. We won't get much more into detail with this particular example about kind of double checking, but again, you know, the reason why I kind of suggest, you know, taking classes in optimization is so that you'll kind of cover this stuff and make sure that your answers are really kind of what you intend. Okay. So I'm gonna show a couple examples of how to solve this type of problem as a as a way to kind of expand your toolbox, just so that you guys can understand ways to kind of solve this. So we'll look at a couple of examples. So Excel and then R, I think these are pretty common for folks to use. And then I'll show an example with a particular optimization oriented platform called GAMS. Okay, any questions about this so far? Okay, so let me jump back over here. Okay, so it's actually pretty straightforward to do. I'm going to set some values. Well, we can start them at, let's say, 0. So I have my P1 and my T2 and my profit. And currently, you can just pick a random number here to start with, although... Oh. Shoot. Yes, sorry. Okay. Sorry about that. So, very straightforward. So in Excel, I just labeled P1, P2, and profit. And then I can set it up so that these are the values here, B1 and B2, that correspond to my P1 and P2. So currently I have them set at 0. I will say the starting point can make a difference, so we'll talk a little bit more about that a little bit later. And then the profit value, if you guys are able to see, sorry, this is a little, can I make this bigger? No, okay. Sorry, this is a little bit small, but right up here, I have our objective function written up. So it's B1, which is our P1 value, squared minus 0.75 times B1, right, plus B2 squared minus 1.1 times B2 plus 0.225. Okay? So all you have to do is like plug in the objective function referencing the values for the decision variables that you want to change. Okay? And the way that I solve the optimization is I go up to, so you may have to add this in under analysis tools if you don't see this thing here called solver, and you just make a checkbox to say enable solver, and then I think it's called solver, or it might be called what if solver, and then you restart Excel and you'll have this. So I'm going to click this button, solver, and here we can see this new text box come up, which is going to help me essentially set up all of the things that I need for my optimization. So it says set objective, and so my objective function, I'm just going to reference that specific cell where I've defined it, right, which is B3. And then I want to minimize it, so you can choose if you're minimizing or maximizing. Did I set it up to be the negative? I did not, so I believe I actually want to maximize this. And I'm going to change my variable cells. And so my variable cells are specifically just referencing the decision variables, right? And so the two cells that are going to change are my P1 and P2. And then you can add constraints if you want later. We're going to do that in just a second. And then I can select different types of solvers. So GRG is going to solve nonlinear, simplex LP is for linear problems, evolutionary is a different way. It's like a genetic algorithm for doing nonlinear things. But GRG nonlinear is what we're going to choose here. And I'll talk a little bit more about the different algorithms later. And if I hit solve, oh, okay. 1 second. Just want to make sure that's, yes, okay. And so let me try something else. That is, yeah. Oh. So in this case, yes. Oh, sorry. I am supposed to minimize it. That's why it wasn't working. My negative null form originally was, or the original one was negative p1 squared. The negative null is p1 squared. So this should be minimized, not maximized. Okay, so let's try that again. Great. Okay, so if you guys remember, so my answer was 0.375 and 0.55. And so here our answer is 0.374999975 and 0.54999954. So 0.55 and 0.375. Okay? Why is my answer not exactly 0.375 and 0.55? That actually has to do with the way that this thing is solving. Okay, so just to be clear, there's a distinction between the way that we had done it, which is solving by hand. And when you solve something by hand in this way, where we are solving for a particular value, right, that is known as solving sort of analytically, right? And so you have like a true answer, but many optimizations are dealing with systems that are too complex to solve analytically, and then so instead what they do is they do it by what we call solving numerically, which is essentially like a smart way of guessing and checking, okay? And if I were to kind of describe this by analogy, instead of solving for the instead of solving the derivative and setting equal to 0 and then calculating what the value would be, a lot of solvers might have some kind of algorithm where they progressively get you closer and closer to the right solution. So you might imagine in that example that I was giving earlier, you know, where when I'm looking at like the convexity, maybe I start at a certain point and I take the derivative and I say, okay, if I go in this direction, I'm going uphill, and if I go in this direction, I'm going downhill. So the algorithm says, okay, take a step towards going downhill. So I step this way, and then I do that again, and I repeat until I'm closer and closer, right? But you may never actually get to the true value, and there are these checkers where it's like, oh, basically, am I close enough? Then I'm gonna stop, right? And so that threshold gets met, and then you end up with solutions like this, which are like very close to the true solution, but not the actual solution. So that's just one thing to keep in mind, is that the answers from your algorithms may not give you like perfectly the right answer, even in the cases where you're dealing with like a convex function, which should technically, you know, have a global minimum that you can get to. Okay? Any questions about that? So next, and I'll post all of this stuff on Canvas so that you'll have access to it. Okay. So this is like a simple example of an optimization in R. And so I set up my function here, and I defined, P1 and P2 in this vector object called P. And then I write out my objective function right here. And we use a function called optim to run this optimization. And if I do this, wrong. So if I run it, then you'll see it returns the values to solve those particular decision variables, right? So x1 or p1 would be equal to 0.375 and p2 would be equal to 0.55. And so those are the answers that we'd expect. And again, these are not the exact values because in this particular case, again, we're doing some kind of gradient descent method where it's doing an estimation, but we're close enough, right? And then, let's see here. So the kind of last thing that I'll say about using different tools to solve it. There are a number of software platforms that are especially designed to handle optimization. So GAMS is an older one. It's called the General Algebraic Modeling System, I believe. And it's literally just an optimization platform. There are other ones so Julia is another common example of an optimization platform. But actually a lot, these days, so GAMS is a little bit older and requires some licensing and that sort of thing. I would say probably in the last like 10-ish years, a lot of the power in some of these like private and commercial-based platforms have kind of tried to, there are communities that have tried to migrate that towards more open source. And so like Python, for example, has a lot of powerful optimization interfaces and solvers that weren't available, like even back when I was in grad school. So, back then, a lot of the models that I use, we ran in this platform, and have since kind of migrated to Python. But one of the nice things about this particular layout is that it's very digestible, the way that everything is set up, right? And so I can define my variables, right? Price 1, price 2, profit. I can define my equations and then write them out in a very analogous way to how you would kind of write it out mathematically by hand. And so that's a very sort of convenient feature of some of these optimization platforms, which is sometimes, depending on what platform you're using, a little bit less obvious, right? So anyways, if I were to run this thing, you end up getting a set of results that ends up looking like this. And after it solves, it will give you, okay, where are we? Yeah, so it runs all this stuff and it gives you a pretty big report out. This is, you know what? This is gonna be for a later example when we add some constraints. Okay, I'll show that. I'll come back to that in a minute. But yeah, GAMS is a nice way of doing optimization on a platform that's like built specifically for optimization. Okay, Before we continue on, why don't we take a quick break for, let's say, 4 minutes, and then we'll reconvene with another example.
Morty's very needy today.
I know it's too nice outside for class. Do you use your iPad? Do you try to extend the screen, or do you just have it swap screens so that it displays through there?
Yeah, I just swapped the screens.
'Cause I know you can do extended display between Mac OS and tablet.
Yeah, I don't know. I
don't know
don't
if
think
you
I've
ever
ever
tried
tried.
that one.
I don't think I've ever tried it because it's so easy to just.
It's called Sidecar. I kind of worked on that feature. Just wondering if you tried it out.
Because with screen mirroring, I do use screen mirroring, and that's like the easiest way for me to do it.
Go on your MacBook and go to open up the displays.
Like here.
Stop here.
All right, let's take a look.
It should be in the top right corner if you get to your toolbar, like the display icon thing.
Oh.
It might be there.
Where's my this guy? Here.
Currently.
But so once I start mirroring though, well, okay, I guess it's in display
Yeah.
settings.
TV.
Link to Mac or iPad. Push through on.
I guess it doesn't work when it's connected to the external display. That's interesting. Thought you'd be able to do it.
I don't want to disconnect
Yeah.
it right now
I know,
because it'll
'cause
stop my
yeah.
recording. But you're saying it's in displays. I can change the
Yeah.
setting to make it so that this is extended.
Yeah,
Cool.
and then you can write on it like
Yeah.
and it would be like through your Mac as opposed to being through your tablet, but you could just bring up like notes on your Mac and you could have it over here and use your pencil. Just an idea. I don't want to
Yeah.
screw anything up, but
So that okay, actually that's good to know. So I can like write on the slides basically.
yeah, and it's just this will act like a secondary display, and that'll be extended, so you could have both displayed, and then if you're outputting, it would have.
Yeah.
both
Okay.
up
I'll try and figure that out today.
there.
Yeah. That would be helpful for some things.
Very neat. Really intense classes if they're about that. You have trouble getting your classes? No. Applied to the, Regents.
Oh, when? Or will?
Figured earlier is better.
Alrighty.
One can know.
Let's continue on. So we're going to we're going to make our optimization a little bit more complicated now. Okay, and so what are we going to do? We're going to add in some constraints this time. So some market shakeups. The local cookie mafia has demanded that you keep the prices of your cookies below 50 cents per cookie in order to ensure fair competition among other cookie businesses. Sounds like a shakedown to me, but yeah, that's a new constraint that we now have to deal with. And so,
We have to ratio your kneecap price.
yes,
cookie
yeah.
ratio.
And then the Milk and Cookies Business Board has come to a decision that the combined price of both items must be equal to 70 cents. So what prices can I now set my milk and cookies to maximize profits? So we are essentially faced with the same optimization problem, but now we have these constraints that we have to deal with. So who can help me out here? How might I write out these specific constraints? Yeah.
So the first one would be P1 must be lower than 50 cents.
Okay. And then did you raise your hand? No? Okay, sorry. Okay. All right, sure. Go
And
ahead
then
with the second
P1
one.
plus P2 just equal to 70 cents.
Yeah, great. Okay, so we're going to add the constraints. We have the general terminology G of x for equality constraints and H of x for inequality constraints. So P1 plus P2 is equal to 0.7 as our equality constraint. And note here we're doing something slightly different than what you said. So P1 less than or equal to 0.5. And so I've added this or equal to. From a mathematical perspective, the difference, right, would be, you know, if it just so happened that 0.5 is the actual optimal value or is the optimal solution for this particular problem, then essentially what you've got going on is P1 would be like infinitely close to 0.5, but not actually equal to it. And that distinction is kind of not so important when you're solving this, but actually adding the equality part of it makes the math and solving it actually a lot easier. Okay. So generally speaking, when we have inequality constraints, you're always going to say less than or equal to or greater than or equal to, even if technically speaking we said below 0.5. Okay? So there are, again, many different ways that we can solve these optimizations. There are different solvers and algorithms that are used to solve these, but when we think about solving by hand, there are some pretty well established procedures for doing this, particularly of specific problem types. This is a convex, nonlinear, general constrained problem, and it turns out that you can solve these. So if you've ever taken macro econ, this is something that is commonly done in some more simple sort of equilibrium functions, of which technically I guess you could call this problem. And so we do something known as a Lagrangian function that's combined with what are known as KKT conditions. It's named after a group of people. I think these are all mathematicians. Karush-Kuhn-Tucker conditions. These are the first order necessary conditions for a nonlinear program to be optimal. Okay, so yeah, once again, what I'm kind of covering here, this would be like a sort of classic example of solving an optimization that you might see in a particular type of optimization class. And so this isn't meant to say like, oh, you could just solve all optimizations by doing this, right? What I'm trying to do here is like introduce one particular tool and show you how it can be used to solve an optimization. But this is not like the complete toolbox that you would need to like fully solve all optimizations. Okay. So this is a Lagrangian function, and so all it is you are taking your objective function, and then I am adding in all of my constraints here, and they are going to be each respectively have a variable we call lambda and mu as parameters that essentially we need to solve for. Okay, so we have our Lagrangian, and so we have how many unknown variables? We have all of our x's, which are unknown variables, and then we also have lambda and mu that we need to solve for. And so in our particular equation, right, we have two decision variables, which are our P1 and P2. We have two constraints, each with a particular, each with a parameter that we have to solve for. So we have 4 unknown values. And so in order to solve that, how many equations do we need? At least. Yeah, we need at least 4 equations. And so those come out of what are known as the KKT conditions. And so what are those conditions? This is the derivative of our Lagrangian with respect to each of our decision variables is set to 0. That's known as stationarity. The derivative of the Lagrangian with respect to our lambda values for each one of our equality constraints, and the derivative of lambda with respect to mu, and those are known as primal feasibility. And this part of it, that's less than or equal to 0, we have something known as complementary slackness. And so the way that you can think about this is kind of checking what happens if the constraint is less than whatever the constraint value is. And this is checking essentially what happens if it's right at that border, right? And so there's a question of if P1 is equal to 0.5, this is gonna essentially tell us that, and if P1 is less than 0.5, that's what this part is meant to tell us, okay? And the last one is mu is greater than or equal to 0, and that's what makes this part sort of feasible. If it's equal to 0, then essentially you're saying that that you're at the boundary, and then if it's greater than or equal to 0, then you're within the sort of allowable space that P1 is allowed to be at. Okay? So let's set this up, right? So now we go from our original setup of our problem with our objective function, which is the exact same as it was before, but with respect to P1 and P2, and now I'm adding in my two constraints, right? With P1 being less than or equal to 0.5, and then P1 plus P2 equals 0.7. And now I do my setup for my, my constraints, right? Where I have my equality constraint as G of P, and my inequality constraint H of P, so that's P1 minus 0.5 is less than or equal to 0, and then P1 plus P2 minus 0.7 is equal to 0. So this is the form of my constraints in the negative null form. It's pretty simple. All you need to do is make sure that you have 0 on your right-hand side. So all I'm doing is P1 minus 0.5 is less than or equal to 0, and then P1 plus P2 minus 0.7 is equal to 0. Okay? And then I set up my Lagrangian. So remember, the Lagrangian is our objective function, so we literally just bring that whole objective function down here, and then I add in each of my constraints, where I have lambda times P1 plus P2 minus 0.7, and then mu of P1 minus 0.5. And if I were to have multiple equality constraints, then you would have like lambda 1 and lambda 2 and so on and so forth. And you'll always, in that way, you're actually always going to guarantee that that you have the right sort of system of equations to solve all of our unknowns. Okay? Any questions about this? All right. So what I can do is I can solve this by hand. And so I can take, as I was saying before, right, my derivative of my Lagrangian with respect to each of my unknowns. So with respect to P1, set that equal to 0, it'll look like this. With respect to P2, equal to 0, it'll look like this. Okay? And I have a whole system of equations, right? And so you can algebraically solve this to calculate values for each of these. And in fact, you will actually come up with two set of values. One where you have a binding and one where it's non-binding. And so that's the case where P1 is equal to 0.5 or where P1 is less than 0.5. Okay, and so when I have two sets of values for mu, P1, P2, and lambda, how do I know which one is the right set to use? Any ideas? What is my objective? To maximize profit. So you will take the values that you solve for, plug them back into your objective function, and one of these is going to be larger than the other. And then that will tell you if the non-binding case versus the binding case gives you more of a profit. Okay? Any questions about this?
You've shown this in Excel as well before. Do you have you would set this up with 4 cells?
I'll show you in just a second.
Okay.
Yep. Yeah. So let's not actually go in and necessarily solve this, right? This is just straightforward algebra. But essentially, you'll calculate all this and be able to show what those values are. And I'm going to show you what the solution looks like across different platforms again, starting with Excel. Okay, so if I jump over here. So this was the example without any constraints. And here I'll jump over to sheet 2. So we can look at our example with constraints. Okay, so we've got our same setup here again, and I'll just zero these out. Profit is here. Okay, so we have a constraint here where we're just writing out the negative null form of these constraints, right? So P1, yeah, sorry, again, it's small, but if you look, it's P1 minus 0.5, and then this one is P1 plus P2 minus 0.7. Okay, so those are our two constraints. Pretty straightforward, right? And here, I'm going to go into my solver again. We're going to do the same thing where I set my objective function to the cell that is defining the objective function. We're minimizing, get it right this time. And then our decision variables are still P1 and P2, which are located in cells B1 and B2. So I have that here. Now, what's different? We now have a set of constraints, right? And so here, for my first constraint, I'm going to select this cell. And then here in the middle option, I can say less than or equal to, greater than or equal to, right? And then I can set what I want the other side of the equation to be set to. So in this case, it's just 0. If you do things in the negative null form, then this will always be 0. Although technically, I guess you could have just done P1 and then set this to like 0.5, right? That would be equivalent. But mathematically, the reason why we do negative null form is actually, historically having to do with the way that we solve these by hand. And I think it's generally good practice to do that. So, okay, so I can add my constraints. So that's the inequality one, and then I have the equality one here, where I reference the particular cell. I change this to equal to and 0, and then I already added it, so I'm not going to press OK, but yeah, so I now have my two constraints. Okay? And if I hit solve, then boom. Okay. So in this case, it's saying, oh, the best solution is to set the price of milk to 0.2625 and the price of cookies to 0.4375. Okay? You can compare to our first problem, where actually the price of both milk and cookies was higher, right? Cookies was 0.375 and milk was 0.55. Here, cookies is 0.2625 and milk is 0.4375. And that will maximize our profits. What does the sum of P1 and P2 have to be equal to? 0.75, right? And so if I sum these, it's 0.75. Is P1 less than 0.5?
Yes.
Yes, it is, right? So both of our constraints are fulfilled, and this will give us the largest profit, or I should say the largest negative profit, because we're doing negative profit here to minimize. And to show you, right, I can manually change this. Okay, like I could set the price of milk to 0.3, price of cookies to 0.3, and manually change the price of milk to 0.4. That would still fulfill both of my constraints. And let's look at what happens to profits, right? So negative 0.19. So yeah, so in this case, the profits become 0.19, which is smaller, or the negative is larger, I guess, but you know what I mean, right? The profit, you get less profit than with the optimal solution, which gets you, 0.0028 more in profit. And so there's literally no combination of values of P1 and P2 that fulfill the constraints that can be larger in profit than this value that we found, okay? And so that's why we call it the optimal solution. Any questions about that? In R, we use, this is an example, it's not the only way to do it, but I'm using a library called R solution NP. Yeah, this is a package that does optimization. So I set up a function that describes the objective function, and then I set up functions for each of the constraints. And then there is there's a function called SOLNP where you can feed it function objects that describe your objective function as your FUN input, equality constraints as your EQ FUN input, and then inequality constraints as your INEQ FUN input. Okay. And if I run this whole thing, right, it gives you a whole bunch of stuff. Yeah, how long it took to run. It gives you the Hessian, which is, okay, it's not a concept I want to get into, but it is a generally an important thing to think about with optimizations. Yeah, it's useful to double check certain aspects of your optimization to make sure that you're doing it right. But I guess the important thing to look for here is, yeah, you have your parameter values of 0.2625 and 0.4375, and in fact, those should match, right? 2625 and 4375 are Excel version. Okay, so a little bit hand wavy, but I'm giving you kind of the framework and the code to be able to do this and to show that, yeah, you can, there's different platforms and software solutions to run this. The one that I was mentioning before in GAMS, here we were able to add in our constraints. I call it the Milk Mafia constraint and the combo package constraint, and you just write it out like this. Price 1 minus 0.5 is less than or equal to 0, and then P1 plus P2 minus 0.7 is equal to 0, and then we solve it with a particular algorithm. I'm using this algorithm called SNOPT, and it will tell me, it gives you a bunch of diagnostics kind of similar to the other, to R that I was showing, but it will also, right, give us this right solution. Here it's rounding to the thousandths place, but it's 0.2625 and 0.4375, same as the solutions that we were getting in the other examples. Okay, so basic idea again is that different platforms are able to solve this, and yeah, you are welcome to use kind of whatever tools that you want to solve your optimizations, but I will leave us with a warning in just a second about that. Okay, so I was talking about sort of analytical versus numerical methods, right? So analytical is this idea where we can kind of like solve by hand, right? Where there is like a true, real solution to our problem that is sort of derivable. And unfortunately, in optimization, it's not like there's sort of a generic solution that you can apply to different optimization problems, unless, for example, it's like a very common optimization problem. And so what is an example of this? So like regression. Who's taken a regression class or knows what a linear regression is? Hopefully most folks, right? So regression, like a linear regression, is actually just an optimization where you are minimizing the sum of the squared error, and the decision variables are your betas, and actually there's a closed form solution. In other words, an analytical solution for solving your betas, which is, you know, xtx inverse times xty, right? So if you've taken a linear regression class, maybe you've heard of this, you can recall that, right? So that is a particular example of a type of optimization that's common enough that enough people have, you know, worked on it, derived it, that there is an analytical solution. But most of the time, for kind of less standard optimizations, if you're doing like systems modeling and you're trying to optimize something, almost guaranteed you're going to be running this through numerical methods. And so these are the iterative methods I was talking about, where you're guessing and checking in a smart way. And you actually need to apply specific types of solvers to solve specific types of problems, right? And so linear program, simplex, and an interior point, those are very well developed. These are that have sort of been worked on the longest and have very sort of robust algorithms, although some of them are still improving to some extent. You have unconstrained NLP, constrained NLP, gradient free, and so all of these methods, you know, descent methods, Newton's methods with constraint, primal methods, Barrow methods. There are many different tools with which you can solve different problems. And so I just want to make sure that, in this class, we're kind of hand waving through a lot of stuff that at least keep some of the stuff in mind, that if you are addressing a particular type of optimization problem, you got to make sure that the tools and solvers that you're using can actually get applied to that. And if you don't do it correctly, you can break the tool, in which case you can't actually solve your problem. And so that can be problematic. But actually a bigger problem is that it'll give you the wrong answer, and you wouldn't know that you had the wrong answer. Okay? Yeah. So there's different types of solvers, and they all use different sorts of algorithms to solve an optimization, right? We're not getting into the guts of like what solvers are doing and how they're doing it. But I just want to show you that it can be problematic to use certain types of solvers for certain types of problems. So let's break Excel. Okay, so GRG solver is known as a generalized reduced gradient solver, and this is one of the numeric methods. And it can be particularly susceptible to certain issues. So let me show you guys a problem. Okay. So, I've got a cylindrical pill. Okay, it's basically a cylinder. And I want to minimize the surface area of this shape. Okay. But I'm going to apply some constraints to it. Okay, so the radius and the height, so dimensional properties of this shape, both have to be positive. That's fine, that makes sense. And I have specific values that I might set for those. But I want to make sure that the volume of this cylinder is going to be equal to 10 cubic inches. Okay, right? So it's got some radius and it has some height, and I want to solve it in such a way that I maximize its surface area, but that the volume is a specific value. Okay? So you might imagine my objective function, right, is to maximize surface area, which is going to be what, pi r squared times height. And then I want to have a constraint that says volume, 2 pi r squared plus height times the diameter, which is, why am I blanking? What's the diameter of a circle again? Pi. No, that's area.
Oh my God.
Yeah. 2 pi r. Yes. So I'm going to add that for the objective function, and then the constraint is going to be pi r squared times height is equal to 10. Okay? So let me just change. So actually, the starting point is actually at the optimum. But let's just change these values. I'll do like 3 and 4. And then let me go to my solver. Not insert, it's in data. Okay. So I've got everything set up. I'm pointing to the objective function and the decision variables, and I have my constraints set up. And I'm going to hit solve. And great. And so it will solve for the values that I was interested in, right? So 1.17 and 2.34, and then this is the only configuration, right, that's going to maximize my surface area with that constraint. Great, okay, seems like it worked, everything was fine. But now let's try, let me try something else here. I'm going to try, we're just going to run it again, but I'm going to try to do this where my starting point is different. So what am I actually doing here? So, you know, pretend we have that same example again where I have like a sort of trench, and then I have to pick a direction to go, and I have to go towards where the derivative is equal to 0, right? And I'm taking a step down the hill. And so, okay, that's fine, right? But the very first step is actually, where do I start in that trench, okay? And that can actually make a difference in your optimization. So I don't remember exactly what values I have to select to break it, but let's take a look. So that one was still okay. So let's do 100, 100? Something like that. Okay, solve. No, that still works. I need to remember what values that I had to use. It's been a while. No. Maybe if I try negative. Something. If it's not this, maybe it's both small. Nope, it still works. Sorry. I'm trying to break it, and I don't remember how to break it. Okay, here we go. I needed to select small values for both. Okay, so I clicked solve. It didn't give me an error, which it will do if you've actually broken the optimization. And it's now provided me what it's calling a feasible solution, even though we can see that, right, the volume isn't correct. And so what's happening here? And actually, did it change the other one? Let me see. No, it didn't. So imagine we were doing this gradient descent thing where I take the derivative, and as I step in a direction, I'm going towards the direction towards like downhill, right? But imagine you have an area that looks really flat, right? Then when I take a step, it may be that threshold that I was talking about earlier is already sort of achieved. And so it says, oh, this is like close enough, right? So there are particular issues with the way certain solvers do things that you can get into trouble because you have these unexpected results. In this case, it's like very obvious, right? But it may be the case that you might be dealing with hundreds or thousands of variables, and you might miss something like this happening when it's telling you that it actually got the right solution, right? Because I didn't get the warning from Excel that this is broken. So that's something that you'll just need to be cautious of as we use these tools. Yeah.
Could I not, like, I mean, even with a lot of values, just select like values that are in the neighborhood of the solution it's giving me, like plus or minus, and see if like how it changes, and I can kind of see if it's an optimal solution, at least a local optimum.
Yeah, well, so there are a number of things that ideally you would want to be checking for, right? And so you could do something like that. The other thing is you got to make sure that your constraints are being fulfilled. In this case, it's not, right?
Yeah.
Like I could say, I could go back and check, but you know, this stuff can get tricky because you might have 1,000 different constraints that need to be fulfilled, and so setting up a checker for all of that stuff, yeah, especially if you're doing it in, you know, a more simplified thing like Excel, it could be a lot harder to do. Yeah, so keep in mind, you know, especially when you're talking about like non-convex things, are you able to, you know, do you know that you actually have like a global minimum solution, or is it just like a local minimum? There's a whole sort of checklist of things that you ought to be thinking about as you get solutions for an optimization. Okay? All right. Any questions? So optimization, it's everywhere, right? Anytime you want to maximize or minimize something. So before this class, who did optimization today? Anybody? Like, I mean, like literally today, who did an optimization? Yeah.
Other ones, like this isn't what I'm used to at all.
Uh-huh. But like, have you yourself performed an optimization today prior to class?
No.
No? Are you sure? How you guys?
It's my internship. It's core planning.
Oh, okay, so you actually literally did like a mathematical. Has anyone? Okay, yeah.
I drove from Berkeley to Davis this morning and I
Yeah.
chose the optimal.
Cool. Right. So who traveled somewhere to be here today? Everybody, right? So, okay, where were you coming from? Okay, so you drove up from Merced today,
Amtrak.
or Amtrak. Okay, so why not like fly down to LA first and then, or you know, like why would you just take the most direct? Right. So you were minimizing the amount of time that it takes to get here, right? And so all of you, doesn't matter if you're walking or biking or whatever, if you took a relatively straight path to this classroom, guess what? You did optimization, right? So really, we are constantly optimizing, and this is like a formalization of that particular problem. But whether we're talking about, you know, any use of resources in kind of like a way where you're trying to minimize or maximize something, that's all optimization. There are problems in optimization that remain unsolved. I was mentioning, right, like your ability to solve like an MINLP, so a mixed integer nonlinear program. There are certain versions of these programs. If you came up with like an efficient solver solution, you would be the richest person, like instantly, like overnight, right? Nobel Prizes would rain from the sky. So, you know, this is a huge field. For those who haven't been exposed to optimization prior to this lecture, right, we are just like very briefly scratching the surface. But because it's so prevalent in systems modeling, I think it's an important concept to at least understand. And if you want to delve more into it, yeah, I'm happy to kind of make suggestions to kind of tailor specific courses to your needs. I just want to close out with a particular example of how kind of I use optimization. So I do a lot of EV research, and so this question of like what happens when you plug an electric car into the grid. The only way to really understand this is to try and simulate the grid in some way, right? And so, you know, we've developed models that try and do this. And they can be enormously complex to actually kind of solve, and they're really large models. But a lot of the fundamentals boils down to actually pretty simple math. This is a kind of simplified representation of the grid modeling that I do. And so we call this dispatch, which is what power plants are turned on in order to provide electricity to serve load demand. And so we have, right, our objective function, and then we have a set of constraints. Our objective function changes with respect to specific variables. These variables tell me how much does a particular power plant turn on, and then how much electricity is sent through a particular transmission line. And what am I minimizing? I'm minimizing the cost to produce that electricity and the cost to ship that electricity, right? So in principle, my objective function is like actually quite simple, right? And then here I'm saying, okay, how much electricity do I have to produce? Well, that's based on my decision variable, plus what I import, minus what I export out of a region. So I say minus C, but you can imagine this is on the other side. The amount of electricity that I'm producing or importing, exporting has to equal the amount that's demanded, right? Pretty straightforward. And then here I have some constraint that like, oh, solar can only operate when there's sun, and wind can only operate when there's wind. And then here I'm just saying, your generation can't be negative, right? And your generation can't exceed what a power plant can produce. And so these are simple inequality constraints, and that's similar for transmission. Your transmission line can't ship more than the capacity of that transmission line, and it can't be negative, okay? So it's a lot of the like data inputs is enormously complex, and the system itself is very large. But here I've got like 5 equations that are essentially describing how our electricity system works, okay? So this is a little bit of a simplified representation, but not too much more simplified than actually we even set it up in some of our models. Okay. Great. So wrapping up for the day, identifying the type of the optimization is probably one of the most important pieces to take away from today, right? Because we are not leaving here with an understanding of all the like math and solvers and everything, but at the very least to make sure you're not using the wrong solver and getting into trouble, make sure that you understand am I nonlinear, am I integer, am I convex, non-convex, you know, all of these pieces are gonna help inform you of the right tool to use. Analytical solutions are always gonna give you the exact right answer. Numerical is only gonna provide approximations, but again, problems are usually too complex for analytical solutions, so we rely on numerical solvers. Yeah, and again, if you are doing optimization more heavily, then I'll suggest some specialized classes to take. And if you want to do optimization, if you want to start getting into it, I think like a class project, right, for your final project would be a good way to kind of explore to see if that's something you're interested in. Yeah, and with that, we're done for the day. See you guys on Wednesday.